Right, test tomorrow. Front side. Okay, I don't want to show it on camera, but I want to read each of these sections off to you, tell you what kind of questions you're going to get here. All right, on the front side, the first 7 are multiple choice. Now, these multiple choice questions are going to come from the properties and the kinetic theory. Properties of solids and liquids, kinetic theory of solids and liquids description, okay, for the most part. There are other couple of questions in there that are going to come from the notes that are in multiple choice format, about 7 of them. Then the next section is about 5 or 6 questions that are just like these. Here. Just like these kind. I'll have this, and I'll have questions underneath it that I'll apply to that equation. All right? And questions like these that are kind of semi-scenario questions, explaining why things are, will do whatever they do at a higher or lower pressure, sea level, that kind of stuff. Now, the next section, there's about 8 or 9 definitions. And I don't give you the definition. There's no word bank. Okay? Now, a lot of the terms are in here, but not all of them. The problem with the definition section, I've seen this many times in the past. One of the reasons why this is one of the lowest grades of the year. Okay? And it's one of the lowest grades because not because this is material that's so difficult. I could probably teach this material, the definitions in particular, that section. I could have a 5th grader memorize those. All right? But you won't. All right? They won't. The 5th grader wouldn't be able to do the algebra and the stuff we did in the calculations. 5th grader wouldn't be able to understand the this stuff here with Le Chatelier's principle. But I could have them memorize surface tension, amorphous, things like that. Okay? They could do better on it than you, and they will, because you won't go home and study. All right? This is the opposite of the last test we just had. The last test, I said the exact opposite. I said if you were here for the review and you got all these problems right, the entire test is problems. It was PV equals nRT and all those problems. There were no questions on the test. I said you don't have to study. You do not have to go home and study. You remember me saying that? If you don't believe me, go back and watch the review for it. This one is the exact opposite. I don't care how well you think you know these things. All right? I don't care how well you do on this one math problem we have. You're going to have to actually study this material. You're going to have to commit it to memory. Not every test is like this, but this one is. Then below that, I've got several more scenario type questions, one of which is a short answer, like not essay, but like several questions would take a paragraph to answer. And it will be one of these kind of things. We'll talk about them when I get to it too. On the back, there's a graph. There's different tests and different questions about that graph. The graph would probably be one of these guys, like a graph like that, or a graph like this. All right, and I'll start off by going over that right now, because that's it. The other thing on the back, by the way, the other thing on the back is blank. Half of it's blank, and that's where you'll put your all the work for the math stuff you're going to do. Okay, the one where you have to actually draw your own graph and fill it in with the delta H or heat of fusion or whatever. All right, let's start with these. I hope you can understand what kind of question I might ask you about this. You should certainly know this is a diagram of pressure versus temperature, and that's the solid, liquid, and vapor phases. Where's the boiling point? It's at 100 degrees Celsius, is it? No, the boiling point is this line. Okay, and it changes based on the pressure. Where's the melting point? Right here. That's that line between solid and vapor, where the vapor pressure of the solid is equal to the vapor pressure of the liquid. Same thing's true when the vapor pressure of the liquid is equal to the atmospheric pressure above it. That's boiling. We redefine those things. Boiling point we no longer believe. You don't believe that anymore. It's just 100 degrees Celsius. That's not what we think anymore. That's not what you should be thinking anymore. This one down here is a graph of temperature versus heat, or time in the case of the lab we did. And certainly should be able to identify all the parts of that. Solid, right? You should be able to know what all these parts are. Solid, liquid, vapor. You should know this is where their melting's going on. That's where your boiling point's going on, right? All right. So you will see graphs like that on the test. You will have to identify them and the different parts of them. Okay? Why is this doing this? Jesus, maybe it won't do it on the next board. I'm not going to get to the next board because I can't hit the thing right. All right, let's review some of the stuff for that. The thing I'm going to go over next are the questions of the review. All right, and those questions, the first ones, concern themselves with an equation like this one: liquid plus energy yields vapor. You have to be, this is the next, and this is the scariest part of this test. What I just said a minute ago shouldn't be a surprise to you. If I don't memorize some definitions, I can't get them right, because they're not terms you're used to using every day. We don't use seeding, nucleation, amorphous. We don't use these terms every day. So if you don't study them, you can understand, all right, I won't do well. But here's the scary part about this test. Even if you study those terms, you won't necessarily do well on the questions like this. I see this all the time with students, especially in a class like this. It's an honors class. You're not stupid. You've obviously gotten where you got to because you're good at memorizing things. But you can't memorize these things. No one's going to be able to memorize what happens when you increase or decrease the pressure or volume. When I ask you scenario questions about a pressure cooker and an egg cooking faster somewhere else, and why alcohol is cooler and why popcorn steam burns, you have to understand it. There's no memorization of all this because I could ask it a lot of different ways. These are just some of the scenarios I can ask it. Okay, so let's talk about what's going on in equilibrium and how the Chatelier's principle applies to this. If I put a bottle of or a jar of water with a lid on it, eventually it will reach equilibrium. The evaporation rate and the condensation rate will be basically the same. All right. If I mess around with that and I increase the temperature, I will ask you on the test what's going to happen. Now, there's a couple of ways you can think about it. You can think about it in terms of common sense. If I heat up water, what am I going to do? And most of you would say it's probably going to evaporate more. It's going to boil. And that's fine when you're talking about temperature. But we must understand it in terms of this equation. I'm making one side too heavy and the other side, or one side too light. What am I doing when I increase temperature? Which of those three things am I directly affecting? Energy. I'm making this side too heavy. And remember Stosh and Stan. Remember my guys walking back and forth between the piles of bricks. Who's going to have to work, because you got two guys going, who's going to have to work faster now to get that back into equilibrium? Evaporation. Okay? All right, so we all agree, I hope, that evaporation will be favored immediately. So I show that with a larger arrow. And I also show, as you can see, there's more vapor molecules now in the more water molecules in the vapor phase. Now, because there's more in the vapor phase, what's going to happen? There's a greater chance of them banging into the surface of the liquid as well and condensing. So the rate of condensation starts creeping up. Eventually, the two rates will be equal. But there's a lot of tough questions I can ask about this. Obviously, the evaporation rate and the condensation rate at equilibrium are the same, but they're both higher than they were before, okay? And they reestablished that equilibrium. Now, that's the easy one. The hard one is when we talk about pressure changes. If I've got a pressure change, like this is a syringe, and I pull back on that syringe, okay, it's at equilibrium. I have to kind of think of this guy. How is he affected? Well, the fact is, pulling back on that syringe, assuming I keep the same temperature, does not affect energy. It does not affect liquid, because liquids are virtually incompressible. What it affects is the vapor, because I'm basically removing vapor, like I did in that vacuum chamber, and I got water to boil at room temperature. Why did I get it to boil at room temperature? Because after I remove vapor, let's say I got a lot of vapor in a concentration, and I have the same number of immediate effect is I have less vapor than I had before. I'm pulling it away. The Chatelier's principle says the system will act to relieve that stress. The stress being less vapor than was there before, it will try to get more vapor. It will favor evaporation. Now, it doesn't do that necessarily by making it evaporate faster. The rate of evaporation, because the temperature is the same, is about the same. It's the rate of condensation that's much less. It's way less condensation when I pull back on that syringe and when I put it in a vacuum chamber. So it's evaporating so fast, the pressure, the vapor pressure of the liquid gets to be equal to atmospheric pressure, and eventually it will boil. All right? So these are the tougher ones. I've got to look at it in terms of who's being affected. In the first case, it was energy. That was easy enough. In the second case, it's vapor. That's not so easy. We don't all have a vacuum chamber or a pressure cooker in our houses. All right? Okay. Now, let's go back to the questions. All right? There you are. Let's start and answer these. And see, now that I've given you that little review, can we answer those same questions? There's my equation. Think of it as a balance. But a dynamic balance, one that's moving all the time. Guys are going back and forth, liquid becoming vapor, vapor becoming liquid all the time. I decrease the temperature. The direct effect of decreasing the temperature is to remove energy. I'm taking energy away. What's it going to try to do? Get that energy back. I hope you all wrote it's going to favor condensation, right? All right. Increasing the pressure. That was the opposite of the one I just did. I'm going to make a higher concentration of vapor. Because I'm increasing the pressure, I have a small space, same number of particles, increased concentration of vapor. It's going to try to get rid of that. Again, it's condensation. Hope you all wrote that.
Wait, so
It'd be reverse. Reverse is condensation, right? And again, there's a lot of ways I could ask that too. Evaporation, condensation. If this had been solid plus energy yields liquid, or solid plus energy yields vapor, then it would have been melting maybe if I was going that way. If it was solid to liquid, it would have been possibly sublimation, going from solid to vapor. Okay, so there's a lot of different things you can call it. That's why I just put forward, reverse, and neither for this one. You can just tell whether it's going forward or reverse. All right, increasing the volume. I pull back on the plunger. I just talked about that. Makes the concentration of vapor less. It's removing vapor. If I'm removing vapor, I'm going to favor the forward direction to put that vapor back in. You notice how this is not a memorization thing. This is understanding it in terms of one simple principle. Whatever you stress, however you stress the system, it tries to get rid of that stress. And finally, increasing the temperature. If I increase the temperature to this guy, I'm adding energy. I'm making this side too heavy. It will try to get rid of it and favor the forward direction. Got it? Okay? Everybody go with that? I didn't see a lot of erasing, so that's a good thing. Now, same basic logic here, using the same kind of equation, but asking more of a scenario type question. There's a lot of ways I could ask these. Same heat is applied to the same quantity of water at sea level and a mountaintop. These are tougher, and here's why they're tougher. I have to first think about what does the mountaintop versus sea level mean in terms of pressure. I hope you all know, we've said it before, at a mountaintop they have less pressure, right? And then at sea level. You should know that. You're up in an airplane, all right, above a certain height on a mountain, you can't even breathe anymore in an airplane. You need oxygen. So there's a lot less pressure, a lot less air molecules banging into each other. So if there's less pressure, all you got to do, again, you can use a little logic, or you can use a little common sense. Or you could apply Le Chatelier's principle. Let's talk about the common sense part. What did I do in that vacuum chamber? Where did I boil water? I lowered the pressure. What did the water do? Boiled at a very low temperature. It was very easy to boil, wasn't it? So where's it going to be easier to boil the water? On the mountaintop, right? So it will reach the boiling point first. It's going to boil at a lower temperature, okay? Because you're already less vapor pressure to overcome. It's going to be easier to boil. So that's nice. Mountaintop's the answer to that one. What about if I drop water or drop an egg into that boiling water? They're both boiling. I drop them at the same time. Well, we just said it was easier to boil the water on the mountaintop, which means the one at the sea level is boiling at a higher temperature. So it's going to cook that egg faster. So this would be at sea level. All right. By the way, that kind of goes to the pressure cooker thing, which comes down here later on. We talk about pressure cooker increase the pressure even more, forcing it that way. So again, you have to overcome that by increasing the temperature. The boiling point is even higher. All right. I'll get back to 7 last, but I want to talk about these first. All right, and then I'll just go. I'm not actually going to do 7. I'm actually just going to set it up for you because I don't really have time, and I want to ask if there's any questions on those worksheets I gave back to you because they're very similar to what you're going to see on the test. Plus, let's face it, the math we have to do in number 7 is really not that difficult. It's tedious. There's multiple steps to it, but there's nothing like PV equals nRT solving for molar mass or anything like that. It's not really that hard, or stoichiometry. God bless you. So, can you explain, now let's look at these equations in other ways. Why is it that sweating cools you off? What has to do with that equation? I would recommend you use that equation as part of your answer. When water on your skin, sweat on your skin, evaporates, it takes energy with it. It's removing energy from your skin. Be careful how you phrase this. In the last class, someone wrote, when they asked the question about their worksheets, well, I said that. I said it releases energy. Is that what it does? Does the water release energy? No, this is not an exothermic reaction. As a matter of fact, it's the exact opposite. When the popcorn steam burns you, it's because when that steam turns to liquid on your skin, it releases energy on your skin. So be careful. It removes energy from your skin because the evaporation process is an endothermic process and it's taking energy with it. There's a big difference between that and releasing energy. Okay, that's kind of, I know it is confusing. I think a lot of people, no, I think all of you probably understand this right now. Can you say it? Can you write it down in words that don't contradict what you think, what you already know? That's the tough part. All right, what else do we have on here? Humid day versus a dry day. You should know the difference between that. Water's condensing faster on your skin on a humid day. So it can't get off. You're not, net evaporation is less, and so it's not cooling you off as much, right? Agreed? Vapor pressure. We had a question in vapor pressure on the second worksheet people were asking me about. Why does alcohol always feel cold? Because the vapor pressure is high. It doesn't have a very strong intermolecular forces. The alcohol is turning into liquid very quickly on your skin, and so it's taking energy very fast away from your skin. Okay. I do not need. You need to study these terms. If you haven't written them down, they're going to be on the. You can watch the video and see them again later on tonight. But we only have a few minutes left. I want to at least set this guy up. I'm not going to actually do it for you. All right, but I'll set it up for you. When you go to do this guy, let's see what happens. You need to first graph it, starting at -38 and getting to 125. So let's take a look. You would draw a graph that would look very much like this, where your lowest point would be, that's nice. Your lowest point would be -38, and your highest point would be, what was it again? 125. You would need to have this drawn for me. If you did not draw one today in the review, I'm not grading the review. If you don't draw one tomorrow, you're automatically losing 5 points. 5 points for not doing that. All right, I need the graph drawn. I need it labeled correctly. Since it's water, what's that temperature going to be? 0. And this is going to be 100. Okay, you need to label all that. You do not need to label solid, liquid. I have that on there. I just use the same graph. You know what you'll need to label is A, B, C, D, and E, like I did in the notes, like you guys did in the homework, and like we did in the lab, I think. Okay? All right, so you label each of these sections, and then we'll have to learn how to do each one. Let's take a look at how you would do each of those sections. Okay? For A, C, and E, here, you are using a completely different equation than you are for B and D. Let's see. B, right here, where it's melting. What are you using? The heat of fusion times whatever mass you have, right? Did you do that? So you should have had, for everybody, what was it, 12 grams, I think, right?
Yeah.
So it should have been, like, the heat of fusion was, like, what, 334 or something? Joules per gram times 12.0 grams. For the heat of vaporization, it should have been, I don't know, what is it, 0 joules per gram times 12 grams. You know what's the only number that's going to show up every single time? 12. Because you have to know how many grams you have everywhere. Here, everywhere. But there, it's a very simple calculation. It's more of a conversion. You're simply multiplying the heat of fusion times the mass, or the heat of vaporization times the mass. Make sure you use the right one. The harder one, and the one that's much easier to make a mistake on, would be the ones where you're doing here, here, and there. Okay, why? Because here, what you're making a mistake on is using the wrong specific heat, which is different every time. And more importantly, I bet you the number one mistake you'll make will be delta T's. People love to just do all of it together. All the way from -38 up to 125. When that's clearly not what happened, and that's why you labeled this A, B, and C. Or, well, A, B, C, D, E. It's why you labeled it differently. Your delta T here is going to be from -38 up to what? 0. Is that what you did? Look at your work. Did you? And did you use for your C 2.09 joules per gram degree Celsius? In this one, your C should have been 4.184, correct? And your delta T should have been basically 100. 100 minus 0, right? And finally, for this guy up here, your C should have been 2.03, and your delta T should have been, what, 25? Is that right? Okay. Now, what if I told you it was steam going to ice? What would the graph look like then? Oops, what? Yeah. If it was steam going to ice, it would look like this. Right? Agreed? You started with 125 and you end at ice at -38. That's what it will look like. Over time, you're cooling it off, you're condensing it, you're cooling it off, you're melting it, you're freezing it, you're cooling it off. That's the whole thing. It's the exact opposite of that graph. And you need to be able to, by the way, will I on the test have all 5 of these sections? Not necessarily. I may not. I may only have up to and including here.
Oh, really?
Possibly.
Okay.
Okay?
Wait, what do you have?
Well, again, I didn't say that. It's possible. I wouldn't have to do all of it. Okay? All right.